Okay, this second slideshow, the point of it is to make sure that you review equilibrium and fully understand it. So I could tell you, I already got my first response back on the form, and people hadn't gotten the video yet and didn't watch the video or didn't review the slideshow well. And there are a lot of misunderstandings. So I want to make sure that people really understand this before they try to answer the questions. So that's one of the great things about the forums is it allows you not only to give me feedback so I can see what you understand and what you don't understand, but also it allows you to see what the correct answer is because it's supposed to give you feedback as you go, and that's how I have them set up. So this slideshow is basically a review of equilibrium, and then we're going to go through some practice questions. So this is meant to be an in-class lecture, so there's some stuff there about, trying to get you to look at how your body stays in equilibrium, because even maintaining your own balance is a constant state of adjustment. So the first thing we have to talk about for equilibrium, and this came up in the last slideshow and it comes up in the third slideshow, is what is an equilibrium exactly? In an equilibrium, you don't have equal quantities. What you have is equal rates of change. So rate is not just the speed at which something is happening, but you're measuring the change of something over time. So one of the easiest examples for this is that speed is the rate of change of distance over time. So you're measuring speed by looking at how much has the distance changed in a certain amount of time. Okay, so this gets a little trickier when you think about a physical equilibria or a chemical reaction, because you have to really understand how are you measuring that change over time to understand how that is a rate change. Okay, so we have to look at this in two ways. We're first going to review physical equilibria, and then in the third slideshow, we're going to get into chemical equilibria. Like I said in the last slideshow, a physical process and a chemical process are very different processes. And so we have to actually take the concept and make sure that we understand the concept in the different frame of reference. So we're going to be talking about rate of physical change and then also rate of change of chemical reactants and products. So let's do the physical review first. So don't forget when I say change of phase or change of state, they mean the same thing. When a substance changes phase or state, there is a period of time where both phases are present at the same time, right? So imagine an ice cube melting. You've got the ice cube, which is still water in a solid state, and then you've got the liquid water of the part of the ice cube that has already melted, right? So here you've got two different scenarios. On the left, you've got a phase change from liquid to gas. This is evaporation or vaporization, right? Where you have some liquid present, and then you have some of that liquid has evaporated and become a gas. This is a phase equilibrium between between liquid and gas. Now over here you have the situation I was talking about where you have ice and liquid water. So some of this water is in the solid phase and some of it is in the liquid phase. So where you have both a liquid and a solid present, you can have the formation of an equilibrium between the solid state and the liquid state. And here you can have the formation of an equilibrium between the liquid state and the gas state. So there's a little bit of a review about vapor pressure here. I'm not going to go too in depth into it right now. There are some videos here that review vapor pressure for you. You will need vapor pressure for the midterm, and there's a graph you have to know, table H. But I don't want to get into it too much right now because I want to focus on the equilibrium. So in a sealed container where the gas can't escape, you will get an equilibrium that will form between the gas particles and the particles that are still in the liquid state. And what this means is that there is the equilibrium is not about the quantity. In other words, how many particles are in the gas state versus how many are staying in the liquid state. What is at equilibrium here is the speed at which particles are evaporating and the speed at which they are doing the reverse process. So remember, evaporation is going from a liquid to a gas. Going from a gas to a liquid is called condensation, right? So you have these two opposite processes happening. If they're happening at the exact same rate, that means that for every water molecule that evaporates, a water molecule goes back to being a liquid. That would mean that in this sealed container, overall, you will never have a change in the quantity of water that has become a gas versus the quantity that is staying a liquid. That equilibrium means that even though there is a constant change, so the thing that flagged for me about the first forms that I got back because people did the homework before the video was released is that people didn't understand that even though equilibrium has been reached, that does not mean that nothing is happening. So the process does not become stagnant. In other words, it continuously is always happening. It's in constant movement. This is why it's called dynamic. When something is dynamic, it's like full of movement. So a dynamic equilibrium is in constant movement. It's constantly shifting in order to keep itself maintained. So in order for this rate, in order for this system to be at equilibrium, every single time a particle becomes a vapor, goes to the vapor state. Let me just change fonts, colors here. All right, so every time a molecule goes to the gas state, a molecule goes back to being a liquid. This is a constant process. It's happening over and over and over again. So it's not stagnant. This is constant movement. The overall result of the movement, though, is that it looks like nothing is changing because you're constantly undoing your movement. So this is the example I always give in class is if you go up an escalator that's going down, right? So say you're at the mall, you know, the escalator, the stairs that go up on their own. If you were to run up the escalator that's going down, right? At first, you have to have like a lot of effort to get up the escalator because it's going in the opposite direction as you are. But if you were able to get to the middle of the escalator and walk at the same speed that the escalator is going down, you could stay in the same spot on the escalator, right? But you are not stagnant. You are constantly moving in order to maintain your position. So equilibrium is more like almost about position, right? Your position appears to not be changing, but you're doing constant work to maintain that, right? And you're doing it by moving up at the exact same rate or speed that the escalator is moving down. Okay, so let's see if I can show you what I mean by my escalator metaphor. All right, now this person didn't intend to do this. It does seem like they were actually trying to go up the down escalator, but you can see that for whole periods of time, even though she keeps trying to get up, if she moves at the same speed as the escalator, she can't go up. She just keeps staying in the exact same spot. So this is the idea, right, of an equilibrium. You could be constantly moving, but if the reverse process is moving at the same speed as the process you're going up, you're going to get what appears to be no movement, even though everything is still actually moving. Okay, so that's basically what we're describing when we describe an equilibrium. A dynamic equilibrium refers to the rate or the speed at which processes are happening at the same time. Okay, so you've got a forward process happening at the exact same time as you have a reverse process happening. That never refers to the quantity, right? The amount of ice and the amount of water in the glass are not relevant in order to establish an equilibrium between the melting and the freezing, or the amount of gas and the amount of liquid. Now, there are three different types of equilibrium that you guys are responsible for. Two of them are physical equilibria, that's phase equilibriums and solution equilibriums. And the third kind is a chemical equilibrium. So the chemical equilibria, we have a whole slideshow we're going to designate just for doing that. This slideshow is really about making sure that before you move forward, you review this idea of physical equilibria, which is from first quarter, and make sure you really understand it. Okay, so let's talk about phase equilibria one more time. In order for there to be a phase equilibria, you have to have both states of matter because you have to have both processes happening at the same time. So, two states of matter, melting and freezing between a solid and a liquid, right? So, the states of matter are solid and liquid. The processes that are happening at the same speed are the melting and the freezing, or a vapor and a liquid. And then it's evaporation and condensation are the two processes. Okay, you've got particles moving between the two phases at the same speed, but the quantities of each phase don't have to be equal. Um, that way, it does look like, though, that the quantities of each phase are staying totally constant. Um, so you've got between a liquid and a vapor. One of the major things that they're going to ask about is this is always funny in pictures and stuff. In order for an equilibrium to be established, the two phases have to be both present. If you've got evaporation happening, eventually all of the liquid will evaporate and all of the gas will leave. So you can't have the bottle can't be open or all the gas will leave. And if you don't have a gas and liquid, you don't have two states anymore, that won't go to equilibrium. So the gas has to actually be trapped in the bottle. So this is for closed bottles. So it has to be stoppered. So here's a practice question for this. An open flask is half filled with water at 25 degrees Celsius. Phase equilibrium can be reached after more water is added, the flask is stoppered, the temperature is dropped, the temperature is increased. Okay, if you just put water in a flask, eventually that water, some of it will evaporate. That means that will go to the gas state. So even if it's not heated, it will eventually, you'll have some vapor and some liquid present. In order for that equilibrium to ever be established, that bottle has to be closed or it won't go to equilibrium. So the answer is the flask has to be stoppered. A stopper is another name for a cork. All right, now we've got what type of equilibrium exists in a sealed flask? If you've got bromine gas and bromine liquid. So bromine liquid is Br2L, Br2G is bromine gas. You've got a liquid and a gas at the same time. And so those are states of matter. You don't have a chemical reaction, and you have no mention of anything dissolving in something else. So it's not a solution. Okay, there is no such thing as a static equilibrium. So this is a great little joke on the part of the regents. Remember how I always tell you there's lots of trick questions? This is a joke. This is like there's no such thing. There's no such thing as a static equilibrium. In fact, I was so confused by this little fake news choices that I even Googled it because I was like, is that even a thing? Like, is there a different type of equilibrium that's static? No, it's not a thing. There is only dynamic equilibrium because equilibrium is not a point where you get there and then everything's equal and you can stop. Equilibrium is a constant shifting to maintain a balance. And so that constant shifting. So I want you to think of this dynamic essentially means that you're in constant movement. So, okay, this is a word, we don't use it this way necessarily in everyday language, but a little bit, right? When a performance is dynamic or a person is in a dynamic, you don't think of them as like a person who just sits around and is boring, right? So this constant movement is in a phase equilibrium because they're describing to you phases with these subscripts. Okay. It's not a solution because solution means that something is dissolving in something else. So, quick quiz. What would that look like if something was dissolving in something else? A subscript for that would be a Q, usually denoting that something is dissolved in water. All right, next question. So that's a dynamic phase equilibrium. All right, so here we've got an equilibrium again. The notation is pretty clear. You've got a liquid here and a gas here. How do I know this is not a chemical reaction? My substance has not changed. Even though it's a substance you're not all that familiar with, actually, you are very familiar with it. You just don't know organic nomenclature yet. Don't worry, you'll know it third quarter. This is ethanol, otherwise known as drinking alcohol. Okay, this is the alcohol is found in alcoholic beverages. So you've got the same substance on both sides. So this is not a chemical change. It tells you up front that it is a phase change, which is a physical change. What's true of all equilibria, regardless of the type of equilibrium shown in the question. So this is one of those things that they do on Regents exams where they make it seem like the question's about a specific example, but the question's not at all about a specific example. How do I know that? Well, first, they told me that this is a phase equilibrium, right? So, regardless of what's going on, if I know the definition of a phase equilibrium, I understand what it is, I should be able to pick this question's answer out. And that's exactly what they're really testing you on here. Do you know what a phase equilibrium is? Right? If you let yourself get all thrown off by the fact that this is a chemical you don't recognize, that's a trap, right? That's designed to make you feel confused. But you know how to read what state of matter this is, and you know what a phase equilibrium is. So, what should you be looking for in your answers? You know that the rate of the forward process must be equal to the rate of the reverse process for this to be an equilibrium. So, there should be no faster or slower, and there should be no stopping because dynamic equilibriums are in constant motion. So that leaves us with choice 3. The forward and the reverse reaction are happening at the same rate. All right. Now let's talk a little bit more about phase equilibria. In this phase equilibria, we've got a solid and a liquid. That means that the water molecules are freezing at the same rate as others are melting. Now we do know that this equilibrium will not stay. It will occur at different points, and then at different points will get destroyed. Eventually, all the ice is going to melt, and at that point, the equilibrium will get ruined because you remember you have to have both states present for the equilibrium to occur. Now, the reason why this equilibrium can't stay is because you have a constant input of energy into the system from the surroundings. But for little periods of time where you have ice and water both present, there will be an equilibrium between the ice cube and the water. Okay, so let's do some practice questions about these types of phase equilibrium. Given the equation representing a phase change at equilibrium, okay, that right away, even if we're not talking about water at all, we know we've got a phase change between a solid and a liquid. My two processes, if I have a solid and a liquid, is melting and freezing. So that means that I must have melting happening at the same rate that freezing is happening. Okay, so again, I can go through these choices and eliminate. Nothing should be happening faster than something else. Okay. Uh, Here's another trick question. They're going to want you to pick this because if you're all right, these kinds of traps are set for those of you who don't study. Those of you who don't study are probably not watching my video right now or getting the homework done. So this doesn't apply to you, but I'm going to say it anyway, just in case it does. If you show up to a test and you don't know what equilibrium means because you didn't study, this trap is set for you. Okay, because you're going to look at this and be like, oh, equilibrium means equal. Oh, so it must be that the masses are equal to each other. No, we just learned that in an equilibrium, it doesn't matter how much you have. What matters is that the speed of one change is happening at the same speed as the other change. And so the quantities will actually look like they're not changing. Just like the woman looks like she's not walking up the escalator, even though she's definitely walking up the escalator. Because she's moving at the same speed of the escalator, she's kind of stuck. So it looks like she's staying in one place, right? So it's going to be that the amount of water that's a liquid and the amount that's a solid is going to stay constant because if every time some of it freezes, the same amount melts, it's going to look like it just stays, right? At the same phase, right? This is why it takes so long, actually, to some degree, for your ice to melt in your glass. Part of it is the high specific heat of water. And part of it is that these equilibriums will occur and they'll resist change until they can't resist it anymore. Eventually, they'll have to give up, but that's okay. They fight the good fight for as long as they can. Okay, so the mass is constant. All right, now, another kind of physical equilibria is in a solution. And that means that you have something dissolving and interacting with water molecules. Please don't forget that when you dissolve something, that's not a chemical reaction. Okay? Dissolving a compound in another compound is a physical change. The particles are still present. They have not reacted with. So let's use an example: salt dissolving in water. The salt's not reacting with the water. It's simply the salt particles are simply going in between the water molecules. Okay. And so that dissolving can have an equilibrium. And the equilibrium is going to be between the um, the solid dissolving and then the dissolved particles recrystallizing. So if you can try to remember if you were in school the day we did the lab where we dropped the crystal into the flask and we watched it crystallize because it was a super saturated solution, that's crystallize, right? You've got um, the dissolved particles going back to their solid form. Okay, so a solution has to be saturated in order for it to reach equilibrium because that means that at that point you've got a little bit of solid sitting at the bottom because no more can dissolve. So remember, these are two-state systems. You need to have a little bit of each thing present. So you have to have a little bit of solid crystal present, and you have to have dissolved crystal present in the solution. Right? So you've got the rate of dissolution being equal to the rate um, of crystallization. So if you've got, it doesn't really matter what chemical they bring up in a question like this. solid KNO3. All your ionic compounds are usually solid salts. This is potassium nitrate. It's an ionic compound. You should recognize it at this point. Okay, if you've got a saturated solution, it will automatically go to equilibrium. And that is because the rate of dissolving is equal to the rate of crystallization. So you're going to see a pattern here where the questions basically all look the same. Oops, sorry. I accidentally stopped sharing. My apologies. All right. They just keep applying it to different situations, and that's because the definition of equilibrium never changes. It's just the process that you're applying it to changes. It's whether or not it's a physical process that's a phase change. Is it the physical process of dissolving something, or is it a chemical reaction? Okay, so it's choice one. The rate of dissolving is equal to the rate of crystallization. Those are your two processes. So you're going to notice a pattern in what I'm saying. You have to have two things present and you have to have two processes happening. So in this case, the processes are dissolving and crystallizing. Those are the opposite processes. And the two things you have to have present are the crystal and the dissolved crystal in the water. All right, which statement must be true when a solution equilibrium occurs? Does the solution have to be at standard temperature and pressure? No. Does the solution have to be super saturated? No. It just has to be saturated. The concentration of the solution remains constant. Ooh, ding, ding, ding. All right, where's the booby trap here? Once again, there's a trap here, and the trap is choice four. And they're trying to trap you into saying that the masses of the two things have to be equal to each other because they want you to fall into that trap of thinking that equilibrium means equal. It does not. The concentration, so concentration, we went over, means the amount. Oh, sorry, we didn't go over it. I made you Google it in the worksheet just to make sure you remembered you knew what it meant. So the concentration is the amount that you have dissolved in the water. So if every time some of it that dissolves goes back to being a crystal, the amount that's actually dissolved in the water won't change because every time one gets dissolved, another one's going to recrystallize. So the amount just stays the same, actually, in the solution, even though there's constant movement. So that means that the concentration of the solution actually stays constant. Oof, let's fix that typo right now. Sorry, guys, I shouldn't do that in the middle of a video, but that was making me crazy. You all know that I get crazy about these things. All right, next question. Which equation represents a system that will reach equilibrium in this flask? So we've got a flask. We've got a saturated solution of sodium chloride. We've got water vaporized. We've got water as a liquid. And so we have got two different systems that could go to equilibrium in here. We've got a physical equilibrium between liquid and gas. We could also have a solution equilibrium between dissolved salt, so aqueous NaCl, and solid NaCl. Okay, so we have to look through the choices and see which one of those do we see. I see, I'm going to write that out for you just so you can see what we're looking for. Okay, so here's the physical equilibrium between two states, phases, right, of matter, the phase of gas, the phase of liquid, right? So that equilibrium would look like this. Liquid. I don't know why I put that in parentheses. That was wrong. I meant to put the gas in parentheses. Sorry. That's one equilibrium that could occur. That's between the states. The second equilibrium that could occur would be between aqueous sodium chloride and solid sodium chloride, where some of the salt is dissolving and some of it is, that's aqueous, and some of it is a solid, like sitting at the bottom of the flask. So that equilibrium would look like this. Notice these are not chemical changes. Both of them are physical only because I have the same substance on both sides. Okay, I don't see this one in the choices. I have NaS solid to NaCl liquid. Okay, so I like to tell you where all the traps are. This is the trap. And the reason this is the trap is because going from solid sodium chloride to liquid sodium chloride is not dissolving it, it's melting sodium chloride. That would be taking table salt and melting it into liquid sodium chloride. That requires temperatures over 1,000 degrees Fahrenheit, and that is not what is happening in this flask. Okay, this is not an equation for dissolving. This is an equation for melting. Here, this equation doesn't even make any sense. Did the salt turn into water? This, no, it doesn't make any sense. Same thing here, doesn't make any sense, right? In an equation of a physical change, the same thing has to be on both sides of the equation. Um, That's not even a valid chemical equation because it doesn't have the same reactants and products on both sides of the equation. Um, all right, that leaves us the last one, the equilibrium between gaseous water and liquid water. So water vapor and water as a liquid. All right, reactions that don't go to completion. So now that's the last definition is chemical equilibrium. In a chemical equilibrium, you've got the two revert, you've got the same situation, right? Um, you're going to have a rate of a forward process being equal to the rate of the reverse process. And then we have to talk about what are the two processes. Here, the process is making the product or taking the product apart and making it back into reactants. So we'll go into this in a lot more detail on the next video. Um, but for right now, what you really need to know, I'm going to actually let you skip this slide because we didn't do acids and bases yet, is that in a chemical equilibrium, it's about making product or taking product apart and making it back into reactants. Now, if that reaction occurs and all of your reactants and products are gases, then there are some um, things that will impact it other than factors like temperature and how much you have. That is also that pressure will affect it. And there's some really famous reactions that are gaseous that we do a lot as examples in equilibria. The first one is usually used in lab demonstrations. However, most of the time when you see this demonstration done, the NO2 or the N2O4 is sealed in a container that you can't open because this is a toxic gas. So nitrogen dioxide is a noxious, nasty gas. It's actually part of air pollution, and it's made as a byproduct of combusting gasoline. So um, this is a chemical reaction where it's chemical. It doesn't look chemical maybe to you guys because the change is not that drastic. But you are making a different compound because you changed the proportion of elements, right? So NO2, nitrogen dioxide, is not the same as N2O, dinitrogen mon. I'm sorry, this is nitrogen, dinitrogen tetraoxide. Okay, so changing the arrangement of the atoms to form a different molecule means you actually changed the chemical. So you can see that it is actually a chemical change. You see the difference in color. Um, and yeah, you see the difference in color. And that has to do with temperature change. The other really famous reaction that we do quite a bit in chemistry is the Haber process. It's sometimes referred to as the Haber-Bosch process because more than one chemist worked on it. In fact, the reaction was pretty well known to chemists, but Fritz Haber became famous for sort of mastering this reaction. And he did that by coming up with a way to manipulate the equilibrium to get it to shift in a way that produced more ammonia. I'm not going to go into this in too much depth because we're going to talk about Fritz Haber some more later on. Um, we also talked about him when we did gases. He's a very controversial figure because his work on the Fritz on the Haber-Bosch process, he won a Nobel Prize for because it makes chemical fertilizer, and that keeps people fed, basically. However, his work for the German government also led to the development of chemical weapons in World War One, and that was a pretty nasty part of the war. It was one of the most horrific parts of the war. Um, and he eventually did do some of the development work. It's a very complicated history. He was Jewish, and his work ended up being used by the Nazis in the extermination camps. The gas that they developed actually was used in the extermination chambers in Nazi Germany. He did not contribute to that work directly, but his research led to the development of those gases. He did eventually leave Germany, but not before he did really a lot of damage. He obviously left because he was Jewish and he realized that Hitler was not on their side, but he was very loyal to the German government and he did a lot of work. He did a lot of really terrible things during a lot of the wars. So if you need some more help for equilibrium and you want to watch another video, this is the link to the crash course episode on equilibrium. But at this point, I think you could take a break and do the homework.